everyone, hjärtligt välkommen to the PhD disputers of Hadi Mohammed on modeling the effects of climate projections on pathogen infections risks in selected water supply systems in Norway. I want to let everyone know that this has been streaming, so if you don't want to appear, you need to sit right on the back over there. But there's signs everywhere that can be recorded. So when you enter in the building, you are being recorded automatically on this building. And I would like to introduce again officially the committee, our external censor, Ekaterina Sokolova from Chalmers University, and then Dr. Ingun Triland from Norges, and they are going to be the first and the second opponent. And I need to be formal just to say, Hadi will present his research now in some 30 minutes. You are free, flexible with the time. If you take too much time, I'll let you know. Then later on, we are going to open first the questions to Ekaterina, the external opponent, and then later on to Ingun. And then after they are finishing with the questions, I will have very shortly questions to the audience as well. Afterwards, we are going to meet the committee and have an evaluation. And hopefully later on, we meet after the meeting at Fyrtårnet, up here, up there. Yes, there, sorry, I was in another room. Up there on the Rundeskua and the up. When we are finished, hopefully around 4:30. There is no time limit. We can take how much time they wanted. So with this introduction, Hadi, please, you are welcome.
Thank you very much for the introduction, and thanks to everyone for coming once again. The title of my thesis is Modeling the Effects of Climate Projections on Pathogen Infection Risks in Selected Water Supply Systems in Norway. And I will start off with a short introduction of the background or the problem and the main aim of the research questions, and I'll quickly take you through the methodology I applied and some overview of the main results. Finally, the implications and some recommendations. There is a consensus among scientists that our climate is indeed changing. And indeed, a lot of compelling scientific evidence are seen currently in recent times in the form of changes in air temperature or increases in average air temperature, occurrence of severe weather events like severe rainstorms and droughts. And in fact, according to the Intergovernmental Panel on Climate Change, the occurrence of extreme weather events are likely to increase in the 21st century. And these weather events, whether it's rainfall, flooding, increased temperature, etc., they are linked to deterioration of the quality of surface water bodies. And these often lead to the occurrence of waterborne infections. And in fact, waterborne illnesses are estimated to represent about 3.6% of daily global burden of disease, with 1.5 million deaths occurring annually. That is according to the WHO. So in order to mitigate the potential effects of climate change on the risks of waterborne infections as a result of drinking water, it is important that key areas of risk throughout the water supply chain or system should be identified so that corrective actions can be taken if possible. Now in Norway, under the current emission rate of greenhouse gases, if the rate is to continue into the future, then by the year 2100, air temperature is projected to increase by between 2.3 to 4.6 degrees. And at the same time, precipitation, rainfall and snow is also expected to increase by 5% to 30%. That is by the year 2100. And one thing that's very important here is that majority of the water supply systems in Norway actually rely on surface water bodies like lakes and rivers. So if these weather parameters, temperature and precipitation are likely to increase, then it calls for action. At least it will be necessary for water supply systems to know the potential risks at different levels. So the main aim of, or the aim of this research was to evaluate the potential consequences of current climate projections in Norway on the risk of pathogen infections from treated water consumption in Norway. And in line with this aim, the following research questions were addressed in my thesis. 1, how could climate change affect temporal variations in source water quality under different climate scenarios? That is the baseline and hazardous situation. 2, what are the likely effects of changing climates on the runoff and discharge of microbial organisms in the catchment of the raw water sources? And then what are the likely effects on temperature and microbial organisms at raw water intake points, or the depths inside the raw water source like a lake? And how reliable are the barrier efficiencies in the water treatment plants in response to any changes in the quality or the microbial quality of raw water that can be linked to climate change? And what are the public health risks associated with climate-induced events in the water supply system? And then what level of corrective actions will be needed? From the onset, the target was to carry out assessments at different climate zones in Norway as much as possible. And as can be seen here, we have like 6 different temperature zones in Norway. But then for precipitation, it's as 11. So the target was actually to, as I said, cover as many regions as possible. But due to challenges with data, I focused on 3 precipitation zones, 2 on the west coast and 2 in the southern part of the country. But the water supply systems that I included in my study were mainly the Ålesund waterworks, which draws water from the Brusdalsvannet Lake. And the one in Oslo, Uset, is the main water supply system for the central part of Oslo. And it also uses water from Maridalsvannet. And the last one was Spadet Diket Lake in Bergen. And among the 3, the Oslo is the largest, with daily average production of around 330 meter cube per day, and serves the population of Oslo nearly 670,000 as at the first quarter of 2018. So these were the main water supply systems that were assessed in the thesis. Now these water treatment plants, that is the Ålesund, Waterworks, Uset, and Svartet, they have almost similar water treatment processes. For instance, they all use rapid sand filtration, although they have varying types. The Ålesund Waterworks uses rapid sand, 1 media. The Uset uses 2 media, whereas the one in Bergen uses 3 media. And they all have the UV disinfection. There is some difference here. For the Ålesund Waterworks, chlorination occurs first before rapid sand filtration, and finally the UV disinfection. Now, in order to assess the potential effect of climate change on the water supply system, I prepared this framework as a guide, because the water supply system is composed of the catchment, the raw water source, the treatment processes, and the distribution network. So I tried to look at some of the potential impacts on the runoff generation in the water source catchment, as well as discharge of microbial organisms, as that can be linked to changes in climate change, changes in air temperature and precipitation patterns or frequencies. And then I also looked at potential effect here in the water source and some aspect of the water treatment. There is one important part here, distribution network, which unfortunately I couldn't account for that part. And then from the results here, I was able to assess or calculate potential risk at the end of the water supply system with respect to the consumption. So in the water source catchment, I applied the hydrological modeling. Within the water source, that is the lake, I applied a combination of hydrodynamic modeling as well as regression and artificial intelligence models. And in the water treatment process or stage, I applied process models to calculate the log reduction or the efficacies of the treatment steps in removing pathogenic organisms from water. And finally, I applied quantitative microbial risk assessment modeling to calculate the pathogen infection risk that will be associated with water consumption both presently and in the future. So a quick look at the various modeling approaches at the various steps. As I said, I used a hydrological model in the water source catchment. And the model used here is the soil and water assessment tool, which is a physically based and distributed hydrological and water quality model. And what happens actually is that because it is physically based and distributed, that means that the catchment is subdivided into different or discretized into different areas of known as hydrological response units. So for each area or for each division in the catchment of the water source, we define different the specific spatial characteristics and weather characteristics, etc., so that flow or runoff generation is calculated for specific areas and finally combined. Now, I applied this hydrological modeling at the watershed or the catchment of Brusdal-Vanette Lake, which is the water source for Ålesund commune here. But we currently, this lake is not gauged. So in order to calibrate the hydrological model, I use a method that is commonly applied in hydrological modeling known as flow parameter regionalization. When we have catchments that are close by and they share similar spatial and meteorological characteristics, it is possible to calibrate the model for a gauge catchment and then transfer the parameters to assess the runoff and other contaminants in the other catchment. So that's the method I applied, and the main inputs were daily air temperature, that is maximum and minimum values taken between 2010 and 2017, and then precipitation data for the same period, as well as climate projections of precipitation and air temperature for 2045 and 2075. And then I use the flow data from the donor catchment, which is the Engeset Dals Lake, also for the same period. Of course, other data included soil type maps, land use, digital elevation models, and I also carried out some sampling of the streams that discharge into the lake in order to compare with the model results. And inside the water source, as I said, I applied the hydrodynamic modeling, and the system I use is known as the Generalized Environmental Modeling System for Surface Water. It is a hydrodynamic and water quality model that relies on the solution of shallow water equations and other auxiliary ones. And the main inputs here were air temperature, pressure, cloud cover, etc., as well as the hydrological data from the calibrated model, because the hydrological model was calibrated for the major streams, 4 of the major streams around the lake. So I use that as an input to assess how these changes in the flow patterns can affect the occurrence of the microbial organisms in the lake, both presently and in the future. And then in the same the water source as well, I applied both statistical model, as I mentioned, the regression, zero inflated Poisson regression, and zero inflated negative binomial regression to predict the occurrence of microbial organisms at the raw water intake points in the lakes or the surface water bodies. Now, I also applied artificial intelligence models for the same purpose. Currently, with the level of advancement in artificial intelligence models, they are so efficient, they are indispensable in terms of modeling very complex systems. But in the case of water supply systems, the application is quite minimal. So I also explored the possibility of applying some of these highly efficient methods in predicting the occurrence of the pathogenic or microbial organisms in water. That study actually involved 2 stages. First, I performed a comparative study where I combined or I used each of these models to predict mainly E. coli, coliform bacteria, intestinal enterococci, and then Clostridium perfringens in the water source for USET, that's Oslo. And the main inputs I used were pH, turbidity, color, alkalinity, water temperature, and catchment precipitation. And based on the performance of the models, I selected one of them, which is the random forest model, to apply in the 3 raw water sources to predict concentrations of E. coli. And in that case, I used turbidity, color, and precipitation as the main inputs. And in the Kioma ray, actually this one, it involved 5 distinct steps. And each of them is composed of different modeling techniques. What I did was I actually wanted to predict based on the current projections of precipitation in the catchment of the raw water sources to predict the potential effect on the pathogen infection risk as a result of water consumption in each of the 3 water supply systems. So I first applied regression models to establish statistically significant relations between catchment precipitation and measured records of turbidity and color in the raw water sources. So I also used climate projections or projections of precipitation and air temperature to adjust the historical records of precipitation that I use in the regression models. So I had my regression models, I adjust my precipitation based on predictions or projections of climate change, then I'm able to estimate or predict potential concentrations of color and turbidity in each of the raw water sources for 2045 and 2075. And at the same time, I also use another scenario using the same method to simulate or to assess the potential effect of the occurrence of extreme weather events or extreme precipitation. In that case, I estimated extreme precipitation as rainfall data that is more than 3 or more than or equal to 3 standard deviations of the recorded precipitation time series, and I use that for the same method to also predict these parameters, stability. So I had them for 2 scenarios. And I also used random forest, as I indicated, to predict E. coli. That was based on the historical records. So having applied this already, I have projections for color and turbidity. So with the model that has already been trained, I was able to predict potential concentrations of E. coli from these ones. From that, I estimated concentrations of pathogens from these E. coli, that's the present ones, or the present concentrations and the predicted concentrations of E. coli. And the main pathogens I calculated or estimated were norovirus, Cryptosporidium, Giardia, and Campylobacter. And then I used process models to predict the levels of log reductions or treatment efficacies of the treatment process for each of the water treatment plants. So I subject the time series of the microorganisms into the treatment processes, calculate raw reductions presently and the future, and then use quantitative microbial risk analysis or models to estimate potential infections risk, both for based on projected temperature, catchment precipitation for 2045 and 2075, as well as extreme precipitation event. Now let's look at some of the main results. Catchment runoff, as I said, it was the model was calibrated between 2013 and 2016, and then I used the remaining 2-year data to test the model. And these are the results for 2 of the streams that were calibrated. And the results indicated that mainly the parameters, apart from the input precipitation and air temperature, the main parameters in the catchment that affects the runoff generation process in the catchment was mostly the forest canopy, that is the proportion of trees in the catchment, and how much water they take, as well as the soil hydraulic conductivity, and organic matter content. And pretty good model assessment or performance measures were obtained, as shown in the R-square and then the Nat-Sutcliffe, which is also another parameter or efficiency used in hydrological modeling. And this is a sample of the predicted or the calibrated E. coli model in the streams. And clearly we can see that the R-square values and NS values were very low compared to the runoff or the stream flow. But then the model was able to predict some of the patterns with acceptable or good accuracy. Then you can also see that here the sampling period between May and September I couldn't actually carry out any sampling. So it is possible that that may have affected the R-square value calculated. So I applied the projected precipitation and air temperature on the hydrological models to predict or to see how runoff in the catchment will change in the future, as well as the concentrations of E. coli. And I realized that here, like the peak flow often occurs in April or in spring, between April and May. That is in the historical flow. But the predictions for future, that is 2045 and 75, indicate that these peak flows could occur a bit earlier in the future. Similarly, when we look at the historical flows, it's usually low in summer, but the future predictions indicate that the summer flow levels could increase. And then for the E. coli concentrations, it was found that compared to the historical pattern of the predictions, the concentrations, particularly in summer, that is currently higher, is likely to be low during summer. But then at the onset of the autumn season, which is the late August or beginning of September, we realize high peaks of the concentrations of the microbial organism in the raw water source. So in actual fact, the stream flow in the catchment is likely to increase in the future, and this has some implications for other surface water bodies in the region as well. And then the pattern and timing of the peak flow, as I described, is likely to shift in the future with higher flow in the summer. And the concentrations of E. coli predicted show that there will be lower peak concentrations in the spring and summer compared to current observations. Now to the water source itself, the lake. The hydrodynamic model was mostly calibrated using water temperature profiles. And in fact, this is at least how far I could achieve in terms of the performance or the calibration of the model. For the E. coli wasn't precisely calibrated in the hydrodynamic model, mostly because the usual pattern of observations in the lake, it differed. The concentration measured by the water treatment plant in 2017 was a bit different from the usual pattern, because typically higher concentrations are observed in the spring season and in the autumn season, mostly due to mixing in the lakes, vertical mixing. And so it was difficult to calibrate the E. coli model. But I realized that once these temperature, changes in temperature result or is associated with dynamics in the lake, and the E. coli model in the overall hydrodynamic model is also coupled with the temperature model, then it's possible that if we are able to calibrate the temperature model, at least it will give us a good indication that the E. coli model was also good. But one thing I observed is that clearly, since very low concentrations were predicted by the model, it means that the discharge or the input from the streams that were used to predict these concentrations, are actually underestimated. There could be other important sources of discharge into the lake that were not identified. So my projections or predictions for the future is actually based on how much was predicted currently, and not necessarily these concentrations that were observed in 2017. And then I also looked at these circulation periods, how the current projections of air temperature is likely to affect the circulations in the lake. And as I said, these circulations are the periods where water temperature at the surface and the deeper parts of the lake are almost equal because of the vertical mixing. And of course, once there's that mixing, contaminants at the surface are more likely to reach deeper zones where raw water is taken. It was observed that compared to 2017, the circulation periods, both the spring one and the autumn circulation, it actually, in 2045, it actually starts and ends almost at the same time. Here it starts, the spring one starts around the mid of March, and it's almost the mid of March. And similarly with the autumn circulation. But for 2075, the circulation was in that the circulation actually starts a bit, or it started at the same time, but then it ends a bit earlier than it used to in the previous years. At the same time, the autumn circulation also starts a bit later compared to 2017, or the current one, and of course 2045. This means that there will be a long stretch of summer condition in the future. And of course, the implications could be sustained water temperature at the surface. And then I also realized that the intensity of the mixing compared to the current mixing, the intensity for both spring and autumn is quite higher. There's likely to be a more perfect mixing in the future. More perfect mixing means more, contaminants getting to deeper parts. And this is a cross-section of the lake showing the distribution or the concentrations of the predicted E. coli in 2075 during the spring circulation, and then 2075. And then the same thing for the autumn circulation period. In fact, as can be seen from the legend, the concentrations are pretty low. But then, relative to the present concentrations, the future concentrations could be significantly high during both the spring and the autumn circulation periods. And so I compared the current temperature in the lake at the surface and at the water intake point depth of 35 meters below the surface. And it was found that by 2075, temperature at the different seasons are likely to increase by some factors. And the largest is likely to be in the autumn. That's at the raw water intake point. And some increases, it's also expected that the surface can be seen here. And for the E. coli, like I said, the predictions for future 2045 and 2075 are mainly based on changes in precipitation. Other factors or things that could happen in the catchment were not factored into this. So this is just a relative proportion by which the concentrations can change. And it was found that in the spring and autumn seasons, the concentrations could, or the average concentration could increase by a factor of almost 3 for both seasons. That is in the future. And then again, some results from the predictive models that I applied in the thesis. Like I mentioned, I applied zero-inflated models, random forest trees, and then the AMPHIS models, and compared them to see how much they are able to predict the concentrations of microbial organisms. Here, these figures show the result for coliform bacteria and E. coli. It was generally found that for the 4 modeling approaches, the AMPHIS was very superior, as can be seen for the testing results for coliform bacteria here. In terms of capturing all the intense variations in the data, whilst the zero-inflated model, the ZIP and then the ZIMP, they were quite good, but first they failed to predict the peak concentrations, which are very vital in terms of optimizing the treatment processes to avoid any potential infection due to water consumption. They were not able to predict these high concentrations, but they were fairly good in predicting the zero concentration and some of the smaller or lower concentrations. And there were some also false positives that they predicted. Similar results were seen in the random forest model. But then compared to the ZIP and the ZIMP models, it was found that this model is more capable of predicting higher concentrations, and the levels of false positives were lower compared to the statistical models. And one thing is, when you a close observation of the assays for the AMPHIS models for both the coliform and the E. coli indicates that the assays is below 0. We have negative 0.5 here, which is not realistic for microbial organisms because they are count variables. The least should be 0. So even though this model was very good for all the water microbial organisms, fecal indicator bacteria predicted, there were negative values that were predicted during the testing. And so, although it has a very good estimation rate, I couldn't take it further. So I used the random forest model for the subsequent studies. And this random forest, as I explained earlier, was used to predict the concentrations of E. coli in the raw water sources for under different scenarios, climate projections, as well as extreme precipitation scenarios. And from this, I had calculated the concentrations of the pathogens. As can be seen, the concentrations of each pathogen was a bit higher when it was calculated under the extreme precipitation event as compared to the normal climate projections. And compared to all the other pathogens, norovirus actually showed a higher concentration in all the raw water sources. But the main reason, I think, was the ratio between the E. coli and the pathogens that were used in the calculation. And then some results of the log removal or efficiencies of the treatment steps for each of the treatment plants. It was actually the log removals were calculated as a triangular distribution. Like I have the mean, I have the minimum and the maximum. Generally, the filters and the UV steps in all the water treatment plants were of acceptable efficiency. But then it was found that the chlorine step in the Ålesund water treatment plant was a bit low in terms of its barrier effect. And compared to the Norges standards, acceptable levels of log removals of each of these pathogens by the water supply systems of this nature, and it is possible or acceptable to say that all the water treatment plants are mostly within the range for each of these microbial organisms. So finally, the pathogen infection risk was calculated from the predicted concentration of the pathogens. And these values, as we see here, they indicate the probabilities that if you consume water from any of the treatment plants, the probability that you can get an infection from maybe norovirus, etc., or the pathogens. So the main benchmark I used to assess the level of the the level of the risk is the WHO, the US EPA value of 1 person in 10,000, expressed as 10 to the power minus 4. So the values that are higher than this value indicates potentially high risks. And like I said from the beginning, this was done, or the infection risks were calculated under two scenarios. First, for the predicted climate projections of precipitation and the occurrence of extreme precipitation in the catchment of the raw water sources. And it was realized that generally under the current predictions of precipitation, the potential pathogen infection risk both presently and in the future may be quite low, even though for some of the water treatment plants, the confidence interval suggests otherwise. But when we look at the extreme weather or extreme precipitation event scenario, we realize that even the median infection risks that are compared to this target may be quite high in case extreme precipitation or rainfall occurs in the catchment of each of the raw water sources. And I also checked the potential effect of any failures in the water treatment steps on the infection risk. So for instance, if UV is operating poorly, what could be the effect on the infection risk presently and in the future? And it was actually found that generally the UV was distinct. And the second one that came all throughout the water treatment plant was the filters. But just as we realized that the log removal or reduction or the capacity of the chlorine system in the Ålesund water supply system was a bit low, it was realized that it has a very low effect on the overall infection risk. So that suggests that optimal operation of the UV step in the water, so all the water supply system is very critical, both presently and in the future. So finally, we found that the spring and autumn peak flow in the streams, particularly the Brusdal-Barnett Lake, will shift. The patterns of the flow will shift in the future, and then there will be changes in the startup period of circulations in the lake. And due to the higher intensity of the mixing in the lake, there will be increases in water temperature, higher concentration of microbial organisms. And generally, smaller water treatment plants with very low microbial barriers could suffer in the future in the event that an extreme precipitation occurs. And from the results, it was noted that viral and or protozoan pathogens may be the main drivers of risk in the future. So some recommendations and further research. Actually, the results indicate that first we need to ensure the improvement of weather stations, because climate impact assessment requires data from weather stations. But I noted that most of the weather stations located around the drinking water sources in the country are mostly not of good quality in terms of the data. And then the water source tributaries should also be sampled if possible. Then this can help such future research. And then source water protection is very paramount, of course, and that can prevent potential effect of occurrence of extreme precipitation. And then I have some further research areas that I think may be necessary to explore in the future. And one of those is that actually, since this result particularly indicate that compared to the projections, the extreme precipitation is more likely to have effect on the quality of the drinking water source. It may be more necessary to carry out the assessment based on extreme weather events alone instead of the projections. And then, of course, the water distribution system can be included. Finally, some acknowledgements. Some of them were actually part of the project: Norwegian Meteorological Institute, Norwegian Water Resource and Energy Directorate. Then I also got some data from these institutes. And of course, a big thanks to the water departments of these communes, the Ålesund, Oslo commune and Bergen communes, for the data and information provision. And finally, to my team of supervisors and the thesis evaluation committee. Thank you.